Hey guys, welcome to Work and Energy Basic Overview for High School Physics 1. We'll be going over some basic concepts and some conceptual example problems. So work is done when force is applied to an object over a distance, and it's measured in joules, and power is the rate at which work is done, which is measured in joules per second. So for example, if I have a box and a force of 6 newtons is applied to it, and it moves 3 meters, what was the work done? Well, we know the distance, we know the force, and the equation for work is force times distance. So we can just simply plug in those units into the equation. So it'd be 6 newtons times 3 meters, which would give us work equals 18 joules. So now let's say the box travels 3 meters in 2 seconds. What is the power? So we know the work already, which is 6 newtons times 3 meters. And the power equation is work over time. So we can just divide that work by the time, which is 2 seconds. And we get the power is equal to 9 joules per second. Moving on to energy. Energy is basically the ability to do work, and there are two basic types of energy we'll be using, which are potential energy and kinetic energy, and they're both measured in joules. So potential energy is energy due to an object's position or condition, for example, the height, or like if a spring is pressed against it. Kinetic energy is energy due to an object's motion, such as like a ball sliding down a hill. So an important law in energy is the law of conservation of energy, which states that energy can neither be created or destroyed, or that the change in potential energy is equal to the change in kinetic energy, or that they both add up to zero. So for example, if I had this ball on a hill and it is a height h above the ground, it would have potential energy right at this point because potential energy is equal to mass times gravity, which is 9.8 times the change in height, and has an inclination to roll down the hill. Now if we applied a force F, it would begin rolling down the hill, and at the bottom of the hill, all the potential energy would have been converted into kinetic energy, and the potential energy at the top of the hill would be equal to the kinetic energy at the bottom of the hill due to the conservation of energy. Now we can also see this modeled by their equations. So as the height decreases, it's directly proportional to the potential energy, so the potential energy would decrease also. And the equation for kinetic energy is 1/2 mv squared. And as the ball rolls down the hill, its velocity increases. And as the velocity increases, the kinetic energy will also increase. So here's a quick example problem for work. A 20-kilogram crate is being pushed 10 meters across the floor with a horizontal force of 30 newtons. There's a frictional force of 10 newtons. How much work does the applied force do? Well, we know work equals force times distance. We know the force applied, which is 30 newtons, and we know the distance traveled, which is 10 meters. So we just multiply those two together and we get 300 joules. Now, how much work does the frictional force do? Well, the force of friction is 10 newtons applied over 10 meters. So we use work equals force times distance, which would just be 10 newtons times 10 meters. And that is equal to 100 joules. Now, how much work does gravity do? Well, the work that the force that gravity applies is not in the direction of motion, so the distance would be zero and the work would be zero. Now that's same for the normal force also. So the work done by normal force would also be zero. Now what is the net work? Well, the net work would just be the work applied plus the work done by friction, and that would just be uh 300 joules minus 100 joules because friction does negative work, and that would be equal to 200 joules. So here's a quick energy example problem. A rock is tossed vertically into the air with an initial velocity of 9.25 meters per second. To what height above the release point will the rock rise? Well, we can draw a diagram where the rock rises a height h above the ground. Now we know it has kinetic energy at the bottom, and all the kinetic energy will be transferred into potential energy, and those two values should be the same. So we can set kinetic energy equal to potential energy, and then we can just substitute in their equations. So now we can just cancel out the mass, and all we need to do now is solve for the change in height. So change in height is 1/2 v squared divided by gravity. And we can just plug in 9.25 meters per second into velocity, and we get 42.78 over gravity, which is negative 9.8 meters per second. So we just solve that, and we get 4.365 meters above the ground. Okay, so this is a quick conceptual problem for energy. A physics class is asked to design a low-friction slide that will launch a block horizontally from the top of a lab table. Teams 1 and 2 assemble the slides shown above and use identical blocks 1 and 2 respectively. Both slides start at the same height d above the tabletop. However, Team 2's table is lower than Team 1's table. To compensate for the lower table, Team 2 constructs the right end of the slide to rise above the tabletop, so that the block leaves the slide horizontally at the same height h above the floor as does Team 1's block. Both blocks are released from rest at the top of their respective tables. Do block 1 and block 2 land the same distance from their respective tables? Well, the answer to that would be no, because block 1 has a greater potential energy than block 2, because it's higher up, because table 1 is higher than table 2, and the slides are the same height. So because it has more potential energy, then it would more energy. The kinetic energy at the end of the table would be greater than block 2, so it would travel a farther distance. So now we just have to write that into a paragraph. Okay, now for part B. Both blocks are released from rest at the top of their respective tables at the same top of their respective slides at the same time. Which block, if either, lands farther from its respective table? Well, the two blocks should land the exact same distance from their respective tables because they have the same potential energy, because they have the same height and they have the same mass, and the gravity acting on them is the same. This means they'll have the same kinetic energy at the end of the table, so they should land the same distance. Okay, now for part two, which block if either hits the floor first? Well, block one should hit the floor first because although they have the same potential energy, the slide is steeper for block one. So it would reach its max velocity first. So it'll reach the end of the table first, so it would hit the floor first. Yeah, that's it. Thanks for watching. Hope you get some of the energy principles now.